You can get Lucene quality while staying in Python, and it changes what baseline means. This is the setup you'll be able to run after this, which builds a reproducible index with language-aware processing and ranks a query to return top matches. I'm Professor Pi, teaching search and IR with simple Python. Search problems start simple and then surprise you. You type a query and expect the most relevant documents first. For many datasets that need fast, robust answers, BM25 is still the de facto baseline. It balances term frequency and document length in a way that is stable across many collections. Lucene has decades of engineering behind its BM25 implementation. The goal here is to get that quality without leaving Python. Intuitively, BM25 rewards documents that use the query terms more often, but it also downweights overly long documents, so a long article doesn't win just by length. Think of 2 short notes and 1 long report. If the short notes repeat the query term more, BM25 will favor them. That behavior makes BM25 a reliable first pass before any fancy neural re-ranker. We will build a tiny, reproducible pipeline. First, we will run a quick pre-built check so you know the environment works. Then, we will create a tiny index from Python that you can version. Next, we will inspect how the text is normalized. After that, we will tune the BM25 parameters to see the effect. Finally, we will enable a simple relevance feedback expansion to improve coverage. Each step is small and concrete, so the whole flow is easy to reproduce. Now we'll run a quick smoke test against a pre-built index. This snippet performs a minimal Lucene BM25 search with Pyserini by loading a small pre-built index and executing 1 query. The LuceneSearcher object is created via from pre-built index, which fetches and opens the Cranfield benchmark for immediate use. The variable searcher encapsulates Lucene's BM25 retrieval with all required index state. The search function takes a query string and returns ranked hits with doc identifiers and scores. The list hits is ordered by decreasing BM25 score. So the first element is the current top match. This compat check verifies your environment can run Lucene-grade Retrieval. The printed top 1 ID confirms a successful query against the pre-built index. Next, we'll make a tiny index from plain Python so results are reproducible. This example creates a tiny, reproducible Lucene index entirely from Python using Pyserini's official indexer entry point. A temporary folder, TD, is created for both the collection and the new index. The code writes a minimal JSON collection file with 2 records containing ID and contents fields, which Pyserini expects. The subprocess run call invokes python-m pyserini.index to build a Lucene index at td/idx using the JSON collection reader. Next, a LuceneSearcher is opened on that path, exposing BM25 retrieval over your locally indexed data. The printed local index docs value shows how many documents were indexed, confirming a successful, reproducible build that you can version and share. Now, we'll look at how the query text is normalized before scoring. This code inspects how Lucene's English analyzer in Pyserini will normalize queries by tokenizing, removing stop words, and applying Porter stemming. The analyzer.fromLanguage function builds an analyzer configured for English, ensuring compatibility with Lucene's pipeline. The variable AZ provides an analyze method that converts the query text into normalized tokens. The variable tokens holds the process terms that will be fed to the retrieval model at query time. Matching index and query analyzers typically improves recall by aligning term variants, like methods and method. If you increase linguistic normalization, precision may drop due to broader matches. The printed tokens reveal the normalization that shapes BM25 matching. Next, we'll change BM25 settings to see how scoring responds. This snippet tunes BM25 in Pyserini via the LuceneSearcher's setBM25 call, and then executes a single query to observe the effect. The variable local references the previously opened local index. The setBM25 function sets K1, which controls term frequency saturation, and B, which controls document length normalization. The search function runs the same query under the new BM25 parameters, producing a ranked list of hits with updated scores. Increasing K1 typically amplifies term frequency impact, while increasing B penalizes longer documents more. The printed top 1 score shows the model's new confidence for the best match, confirming parameter control over BM25 scoring. Finally, we'll try a lightweight pseudo-relevance feedback expansion. This example enables RM3 pseudo-relevance feedback in Pyserini to build a stronger lexical baseline. The setRM3 function on the LuceneSearcher expands the original query with top terms mined from the highest scoring FB docs, keeping a mixture controlled by original query weight. The variable hits then reflects a new retrieval under the expanded query. This is a standard production-grade way to boost coverage on sparse lexical signals before neural re-ranking. Increasing FB terms broadens expansion vocabulary, but may dilute precision. Increasing FB docs mines from more pseudo-relevant texts, which can help or hurt depending on the collection. The printed RM3 top 1 indicates the current best document under RM3 expansion, demonstrating a complete, reproducible baseline. Map to a real project. The tiny index and 2-document example is a stand-in for your real collection. The same steps scale. Create a JSON collection that describes your data. Build the index. Confirm analyzer choices. Tune K1 and B on held-out queries, and optionally add RM3 before passing candidates to a neural ranker. Recap. What this is: a practical way to run Lucene-grade BM25 from Python and reproduce your baseline. When to use it? When you need a solid, fast lexical first pass or a stable baseline for evaluation. One caveat: heavy normalization and blind expansion can increase recall, but sometimes reduce precision. So validate on held-out queries. Next step: tune BM25 K1 and B on a small validation set to find the sweet spot for your collection. If practical IR helps you, subscribe and watch the IR videos.